ourselves the question: can we drive the state of the system to an equilibrium state in finite time by choosing an appropriate control input? Right, as we discussed an automotive example. The question is, like suppose if we have a path and I have a vehicle, right, which is deviating from the path. Okay, so let us say at this time I wanted it to be here, so it is having a error in the lateral direction, and it's also having an error in the heading. Okay, so we could formulate the problem in terms of these error variables. Ideally, these error variables will be zero. So in essence, that is our origin or equilibrium state, right? So the question is, when perturbed from this equilibrium state, can I come back to the equilibrium state? Okay, so that is the broad question we ask ourselves when we look at control. So today we are going to learn about what is called as full state feedback. So what is this full state feedback? Let's imagine that, we first consider a MIMO system, then we'll come to the SISO system. So let's say this is our state equation and output equation, right? X dot equals AX plus BU, Y equals CX plus DU. The question is, can we design a control input U, which is of the form K times X, okay? Plus, it can also involve an extraneous input R of T, okay? That is not necessary, optional. This extraneous input is optional, okay? But the main aspect is that we should have this K times X of T, okay, as part of the control input. So if you and I are able to find such a control input, which is proportional to the state vector, right? And K being what is called as a controller gain matrix, okay? So in the case of a MIMO system, the question becomes, how do we design K, right? Such that, we assure closed loop systems stability and performance. So K contains various controller parameters, right? So see, for example, when you and I looked at, this one, right? So, PID control, we would have we would have looked at, the fact that we had KP, KA, KD and all, right? As parameters, right? So similarly, in the full state feedback controller, we'll have the matrix K, the controller gain also to be filled with real numbers, right? That we need to find out. So to assure closed loop stability and closed loop performance. So how do we go about it? Okay. So what we do is that we substitute U equals Kx plus R. So this is our input U. So then we get the dynamics of the closed loop system. Okay. So the state equation for the closed loop system becomes X dot equals A plus B Kx plus B times R of T. Okay. So this is what is called as a closed loop dynamics. So then in this equation, the matrix A plus BK is what is called as a closed loop state matrix. Okay. So there is a state matrix associated with the closed loop system. Now for closed loop stability, what do we need? The condition is the same, okay? So whichever system it is, right? So we write in the state space representation. For stability, we need all the eigenvalues of the state matrix to be in the left of complex plane, right? So now we need the closed loop state matrix to have eigenvalues in the left of complex plane. So the broad idea now is the entire design problem is to find this matrix K such that the spectrum of the closed loop state matrix, okay, ACL, becomes lambda 1 desired, lambda 2 desired, up to lambda n desired. Okay, so let's say we consider the nth order system. We want the eigenvalues of the closed loop system to be at lambda 1 desired, lambda 2 desired to lambda n desired, right? This is similar to closed loop poles. Okay, so we want to place the closed loop poles at specific locations. Similarly, you and I want to place the closed loop eigenvalues at specific locations, right? So the question becomes, how can we design this control gain matrix K such that we are able to place these closed loop eigenvalues at the desired location. Okay, so that is what Am I audible? No. Okay, I think there was some perturbation in my network. Am I audible now? No, sir. Hello.
Yes, sir.
Yes, sir, you're audible, sir.
I'm
You're
audible.
audible. Yeah.
I hope there was some perturbation in the network. Right. So consider a single input, single output system. We know that the state equation and the output equation are this. Here the what to say, the fact is that like now we have an input vector, right, in place of an input matrix. And consequently, what happens is that like we essentially want to now gain matrix, we want to find a control gain vector K such that the input U for the closed loop system is of the form U equals K dot X plus R. Okay, so so why are we taking the dot product? Please note that like you and I for a SISO system, the input U is a scalar, right? Whereas the output, the state is a vector. So to get a scalar from a vector, we take the dot product of the gain K, right, with X, with the vector X. Okay, so R of T is the external symbol. In most textbooks, they would write K transpose X of T, right? So we have already discussed this, right? If you recall our notation, right? So you and I prefer to use, or I prefer to use the dot product notation. Some people will write this as a row vector and this is a column vector, and if you multiply, we get a scalar, right? So that is the equivalent notation also some people use. Okay. Now, what we do is that like we substitute U of T in the what to say back into this state equation, okay, to get the closed loop system dynamics. If you and I do that, what will happen is that if we do the algebra, okay, we get the closed loop state dynamics to be X dot equals A plus B outer product K X plus B times R of T. Okay, so and the closed loop state matrix becomes A plus B outer product K. So now what is this X within a circle? This is what is called outer product of a vector or a tensor or a dyadic product. Okay, so if you consider vectors, there are three products, right? You and I know scalar or dot product, okay, which is A dot B. So how do I take the scalar or dot product of two vectors?
AB cos theta.
AB cos theta. But if we are given the elements of the vectors A and B, what do we do?
We just multiply the element and corresponding of like same like what I mean to say is the same 1 1 with 2 1 like that in that sense.
Okay, okay, understood. So essentially, we multiply the corresponding elements or components in the vector, right, and then add them, right? So that's how we get a scalar, right? That is a scalar or a dot product. Then we know the vector or the cross product, correct? So that's also something which you and I would have learned. So what is this vector or cross product? It is essentially A cross B, right? So what is, how do we calculate A cross B?
It becomes a I cross J is equal to K cross J is equal to like that. It'll become like a what I mean to
Sir,
say.
I cap minus J cap plus K cap.
Yeah.
So yeah, we typically like calculate the cross product by forming a determinant with ijk in the first row, and then we put in the what is
Yes,
the
sir. Yes.
element and calculate the determinant, right? So in fact, the interesting fact is that like it so turns out that you and I can calculate cross product as it is defined only for vectors of dimension 3. Okay, we can calculate cross product for 2-dimensional vectors or 4-dimensional, 5-dimensional, and so on, right? So that's an interesting tidbit for us. Okay, but then like like we essentially form a vector, right? Through by looking at the cross product, okay, or the vector product as the name indicates. Now, the third product, which we may not have commonly encountered. See, these things we study in high school max may not have commonly encountered is this outer product or tensor product or dyadic product. So what is that? That is denoted by the symbol cross within a circle. See, dot product is we have a dot, cross product we have a cross, outer product we put a cross, but we put a circle encapsulating the cross. So what we do is that, like, if we take a simple two-dimensional example where we have this vector B with elements B1 and B2 and K with elements K1 and K2, the outer product of B and K, which in this case is this, what we do is the following, right? So we form a matrix whose first row is B1 K1, B1 K2. That is, we take this B1, multiply it with each individual element of the vector K, and then form the first row. In the second row, we multiply B2 K1 and B2 K2. Okay, so that's how we get a matrix, like which essentially becomes part of the which becomes the outer product. Okay, some people will as a mnemonic, like to essentially do it easily, they will do it this way. They will write as B times K transpose, which will also give you the same answer. Okay, so essentially you will get B1 K1, B1 K2, B2 K1, B2 K2. Okay, so this is how we calculate the closed loop state matrix. Okay, ACL, which will be A plus B outer product K. Okay, so in the next class we will be doing examples. So this thing will become even more clear, right, as we go along. Okay, in the next class. Okay, so I hope it's clear how we calculate the outer product or the dyadic product or the tensor product. Okay, by using this equation. Now, if we look at this particular thing, what happens is that, like, for the the single input, single output system, when we do full state feedback, the closed loop state matrix comes out to be A plus B outer product K. So the control design problem is to find the control gain vector K such that the eigenvalues of this ACL are prescribed. Okay, so we need the eigenvalues to be in the left of complex plane at specified locations so that you and I are able to guarantee both stability and performance. Okay, so that is the idea. All right, so how do we do that, right? So that is what we will be learning in the next class when we do a control design problem. But then this is where the result on controllability becomes very useful for us. So it so turns out that if the system is completely controllable, if we have a MIMO system, then there exists a solution to this problem. That is, you and I, what happened here? You and I will be able to find, 1 minute, sorry. Something went wrong. Okay, you and I will be able to find a control gain vector K such that we are able to get close to stability and performance. For single input, single output systems, there is a very interesting result. If a SISO system is completely controllable, in addition to K being existing, there is a unique K. That is, there is a unique control gain vector K such that we can place the closed loop eigenvalues at the desired locations. Okay, so that is another important result as far as SISO systems are concerned, and the fact that the system is completely controllable. Okay, so for this reason, see, 2 points. Why is it called full state feedback? Because we are calculating U of t to be equal to K dot X. Okay, R of t is typically optional. Okay, so we can include R of t or we will not include R of t. Okay, this is optional. Okay, but this K dot X of t, we can immediately see that the control input requires the knowledge of the state vector X, right? So to implement this controller, you and I require knowledge of all the state variables X. Okay, So that is why it is called as full state feedback. Okay, so I hope the reason behind the name full state feedback is clear, right? So why is it called full state feedback? Because you and I need complete knowledge of all the state variables to implement this controller, okay, in real life. Okay, so that is why it is called full state feedback. And the control design problem boils down to finding this the gain vector k such that we are able to place the eigenvalues of the closed loop state matrix in desired locations. Okay. For that reason, this problem is also called as the pole placement problem or eigenvalue placement problem. Okay. So essentially, this is a problem of placing the eigenvalues in the desired location is also what is called as a pole placement problem. Okay, so I hope it's clear why we call it as the full state feedback problem. That is, we want to calculate the control input by taking all the state variables with their knowledge. We go and calculate the control input. Okay, that's why it's called full state feedback. Okay, so and since the objective is also to place the eigenvalues of the desired location, right, to ensure closed loop stability and performance, we call it as the pole placement. Okay, so we want to place the poles at these locations. Okay, so this is the background behind full state feedback. This is a very common controller used in just like PID in transfer function, right? Full state feedback is a very common choice of controller used in the state space representation. Okay, that is why we are learning it. Now, I'm going to introduce you to an example, but then we will I'll look at it in the next class. So what we do is that we consider a second order system. Let's say this corresponds to some steering motor or or even like a brake system or any other aspect, right? So what we do is that we essentially have full state feedback, to be such that we want to start from the mathematical model of the system and then go ahead and construct the controller. Okay, so that's what we want to do. All right, so let's consider this second order term, second order system, right? Essentially, if we consider the state equation to be x dot t equals 2, 3, 0, 1 x of t plus 1, 1 u of t, and y of t is 1, 1 dot x of t. Okay, so this is the system equations. Okay, so what I'm circling here. Okay, so that is the system equation to begin with. Now, the question that you and I are posed is that we need to design a full state feedback controller that would place the closed loop eigenvalues at -1 plus or minus j. Okay, so these locations are decided by the designer based on two considerations, right? So we need closed loop stability and closed loop performance, right? So that's something which we have been learning throughout, right, when we design the closed loop control system. Okay, so we need to satisfy both these requirements, and based on these requirements, we want to place the eigenvalues at -1 plus or minus j. Okay, so that is the problem. What we will do is that we will do this problem in the next class, but you can go through the solution. Okay, I will go through all the steps with the class, but once again, when we do the problem, we first start off in the state space representation. You and I will always start off with calculating the equilibrium state of the given system, figuring out whether that equilibrium state is stable or not by looking at the eigenvalues of the state matrix. And then we go and calculate K, okay, which is the control gain, so that we can place the eigenvalues in the desired location. Okay, so we will do this example problem next Wednesday, and while we do it, we will also understand the finer steps of this process. We will also understand why the controller canonical form, right, becomes very important. Okay, so that is also something which we will realize as we when we do this particular work. Okay, fine. So that's what I wanted to convey to you in today's class. Any questions on the material that we learned in today's class? And in response to the query, it came right. So, for example, practice for the final exam. So, the example that we do and also the homework problem that we do will give you enough practice, right? I hope that's acceptable. Okay. Yeah.
So just one fundamental question from my side. Am I audible?
Yes, please.
I am actually not so familiar with tensors. So this concept of tensors, where and all we typically use.
Okay. So tensor. Let me put it this way, Prem. So tensor, in a simple way, you can think of it as a matrix. Okay. Essentially, in fact, what I can do is that even I can share videos on linear algebra that I teach voluntarily with to IITM research scholars. Right. I used to teach it on weekends, and during COVID, I recorded it. So Prem, if you can send me an email, right? I will just, all right, let me see while we are talking. I can share it with you so that all of you can watch it, right? And learn about linear algebra in general. If you feel you want to learn it, okay, it's completely optional. Since this question came, I am just sharing that link with you. Okay.
Sure, sir. I'll send a mail.
I think don't worry about it.
Everything is done.
No, 1 minute. Just give me a minute. Anyone with this link can view. Okay, copy link. Yeah, I am just pasting or including the classroom stream. Okay, a link. 1 minute. Just give me a minute, Spray.
Sure, sir.
So I have posted a message in the Google Classroom frame with a Google Drive link. Okay. So where during COVID, the same optional course which I used to voluntarily teach to our students, I started recording, right? And then, but it's incomplete. See, what happened is that before I could complete, my administrative responsibilities increased. And I want to complete it once the loading decreases a little bit, right? So, but then you can watch these things, Prem. You will get a broader idea about vector spaces, matrices, tensors, and so on, right? But if I have to explain tensor in a very simple way, once you fix coordinate systems, a tensor takes the form of a matrix. Okay, so a matrix is nothing but the components of the tensor, right? A tensor is an abstract quantity. You get a matrix once you want to express components of a tensor, right? I hope at a broad level I have answered. So that is why a tensor and matrix are used interchangeably. Okay, yeah.
Understood, sir. Yeah, thank you.
And Prem, are you able to access the link in the Google Classroom stream?
Yes, sir. I'm going through that only. Just a minute.
So no problem. Once again, to everyone, that's completely optional. Since this question came, I'm just sharing it so that you can watch that, right? So okay.
It's accessible, sir. Yeah.
Oh no. 1 minute. I think I shared the wrong link. 1 minute. Let me edit the thing.
Yeah, it's for the entire linear algebra.
No. Actually, I have shared some other thing also. 1 minute. Let me edit. Okay, please delete this link. Okay, that was unintentional. Sorry about that. What I will do now is share the current. Okay? Yeah. Please, I have posted an edited message frame. Use that. Okay. Yeah. Please neglect the previous message. Okay. Yeah. Right. Yeah.
Got it, sir.
So in this link, you will see 12 videos. As I told, I could not complete the course, and you will also find handwritten notes of linear algebra. Okay. So I think that will be quite useful for you also if you are doing computational methods and so on. Right. You will end up using a lot of ideas from linear algebra and matrix theory.
Yeah, sir. I think next semester we might be having that paper. So
Yeah. So this is from a very abstract perspective. So those who are interested can watch. Right. Most welcome.
Thank you so much.
But kindly do not change it. Because you are most welcome to download them and watch them offline also. No problem. But please, request you to keep all the videos there. Right. Okay. Any other questions? So once again, the application of this full state feedback to automotive control will we will learn when we are doing the second case study, right? I think it will become clear how we use a vehicle dynamic model and then develop a state space controller, right, for that. Okay, so once we do the case study, we will get a better perspective. Fine.
So just one basic question. If the value of k is going to be only one number, say, I mean, in the problem that you're solving also, k turns out to be 2.5, minus 2.5, but we're writing as k1, k2. Why two values have to always?
So, okay, Prem. Okay, so I'm preemptively going to the solution. This is a unique case. Okay, it just turned out to be this way. Okay, the k1 is not equal to k2. All right. It's
Yeah,
so
for the complex conjugate based lambda, we are getting.
no. Okay, I think that's a good guess, but not that also. Okay, it just turned out by chance. Okay, so see, when I constructed this problem with random numbers, it is just a matter of chance that it came out to be equal. Okay, so
Okay.
yeah, so I think I think that's a good point. It's just I would say very strange occurrence or very strange chance that this happened. So we should not be generalizing this, right? So it's a very specific case. Okay? So when you do the other homework problems and all, you will get a different result. Okay. So we will, I think in the next thing when you do, yeah, here you see that you get minus 4 minus 1, right? So the next problem, right? Okay? The same.
Yeah, okay, sir. Yeah.
Okay. So this exercise will be a homework 5. Okay. So we will anyway we'll discuss this as we move forward next class. And how is that project one going on? Is everyone on track to complete? I think Abhinav told that deadline is 5th, right? So is everyone on track for submitting that?
Yes, sir.
Yes, sir. We have tried to complete it. We'll discuss and submit.
No problem. So any issue you face, you please contact Abhinav. He will certainly assist. Okay.
Just for information, we have discussed a bit among ourselves for what I mean to say is the equation that we have got is different for everyone. But what I mean to say for the clarity of purpose and solution, we have had a session with among ourselves and we try to figure out how to proceed in that. So that is okay, na, sir?
Yeah, no problem, Roshan. See, I in fact encourage team learning. Okay, so that all of us learn from each other. But I want everyone to solve individually. So
Right,
we can always work as a team, learn from each other. I would encourage it particularly at the postgraduate level. See, this is a graduate level course, right? You are doing an MTech program, and you are all industry professionals, right? So I would strongly encourage you to work as a team, right,
Yes,
and learn. Okay, but at the end of the day, kindly submit your own solutions, right? See, in fact, Roshan, like that brings to a very philosophical point. That is, see, when we give such questions, see, for example, even here, I have given a question to which I know that there is a solution, there's a unique solution, all of us should get the same answer, right? But
Right.
really, it's not like that. So even when you do the brake control design problem, depending on what performance metrics you choose, right? What value of K you choose to, choose, right? Or, essentially also adopt, right? So the point is the values of the controller gains or the controller parameters will certainly change. Okay, so that's something we need to remember. So what do I mean to say? Even if you have learned the process together, if there is scope for each one of you to choose different, let's say, performance criteria, right? Try it out so
Right,
that you will get different answers, but then you will have understood the framework better. Okay, so
Exactly, sir. Basically, when we're discussing about among ourselves, we could figure out that the concept-wise, what Sai has taught us, or what they guided us actually, we were able to grasp the concepts, and almost all were in agreement what to do. But since
okay.
few of us is not so conversant with MATLABs and all, no? So it was just a like we have some people like Rahul and Vivekanand. They are very good at MATLAB.
Okay,
So
okay.
they would help us with some, like I would say, how to proceed in that way, how to
Very
write
good.
codes, and that's it.
Yeah, yeah. I think that's very nice. So you should certainly learn from each other. Okay, I would strongly encourage.
Thank you, sir.
So any other questions? So Arunachanam, is everyone present today?
Yes, sir. Everyone is present, sir.
Okay, I'll mark attendance for everyone. So that's done. So yeah, if there are no further questions, maybe we can close a few minutes early today. And use the time to also complete your project work. Like if you want to discuss something.
Yes, sir.
And submit the project report. Okay.
Thank you, sir.
So once again, I will meet you next Wednesday at 5 p.m. Next Monday and Tuesday, Sai Abhinav will conduct the sessions for
Yes.
project. Okay. Yeah.
Okay.
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 Thank you, sir.
Bye-bye. Bye.
Thanks a lot, sir. Thank you.
Thank you, sir.